Welcome back everyone. My name is Pedram and this is where we do machine learning codes and concepts. Let's get started. Alright everyone, let's do the Python part for our module number 6, regularization and penalized regression. So today we're going to do Ridge, Lasso, and ElasticNet in Python using Sklearn package, and at the end of the day I'm going to show you how to do it with Pycaret. If you haven't watched the theory lecture, please go ahead and do that before watching this one because you need the underlying theory to understand the code deep down. The goal is to replicate these plots that we talked about it last time. So for example, for the ridge regression, we work with the synthetic data coming from this true model. So this was the true model, right? And then we saw how ridge was able to get close to these coefficients by tuning the hyperparameters lambda, right? So in Python, it's called alpha, but this is pretty much the same, just different Greek letter. This is our shrinkage parameter. And then, so we're going to replicate these, path to for the coefficients, and then we're going to do the same exercise for Lasso and ElasticNet. Okay, so here's where you can find the code. Go to the machine learning course, and then lectures and code. Module 6, and these are two files that I'm going to cover in this video. The first one is working with the synthetic data. This is exact replication of what we saw in the slides, and then the next one is going to be basically applying the penalized regression to Boston dataset. Okay, so let's starting with the synthetic data. Okay, penalized regression. So as we saw in the theory lecture, imagine this is the true model, x plus 2x squared minus 3x cubed plus some noise. And then and obviously this is our target variable, and the features are x squared, and x cubed, right? And we're trying to see how close we can get to this model using 4 models actually. The linear regression, we're going to use it as a benchmark, ridge regression, Lasso, and ElasticNet, okay? So let's go ahead and do that. We're going to import the libraries. Actually this is, if you open it from my GitHub, so make sure you make a copy to your own drive, but here I'm not going to make any changes, so I'm going to run it anyways. But make sure you work with your own version, you copy to the drive. Okay, so let's set the random state to 1000, just if you want to get exact same the outputs as I do, so I encourage you to use this random state. We're going to work with this synthetic data that we created last time. So yeah, this is the head of the data set. Again, we have 5 features, x squared, x to the power of 3, 4, 5, and a target variable. Okay. All right, let's look at the scatter plot quickly. And this is a relationship between y and x. And apparently something to the power of 3 is going to do the job for us. But let's see how successful the penalized regressions are to just getting rid of x4 and x5 by sending W4 and W5 towards 0 or setting them exactly to equal to 0, because we know the true relationship is this. We know that we don't need x to the power of 4, we don't need x to the power of 5. But let's see how penalized regression is going to handle it. And remember, this is penalized regression, so we need to normalize the features. As I talked about it in the theory lecture, we have to do that because for example, in Lasso, when you're doing gradient descent, we need to make sure that, computationally it's more efficient, right? And for ridge, it really doesn't matter because it's going to use a closed form solution. But for Lasso and ElasticNet, it's going to be more important to scale the features. All right, so for that reason, let's go ahead and import our standard scaler from Sklearn. So we want to scale these features, right? So let's go ahead and train it. This is an object. I'm going to fit transform to the entire data. So for now, we're going to use the fit transform to the entire data. And then for the Boston data set, we're going to use train test. Okay. So we have 100 observations, and obviously the scale version has 6 features, right? So we are scaling everything, including the target variable. All right. So yeah, here again we can put it in a nice data frame. I'm gonna skip this part because we have seen this multiple times before. But feel free to pause the video and then try it on your own. So at the end of the day, we scaled this data frame. We went from this to something like this. So obviously these are the scale version. All right. Then we can look at the scatter plot of the scale version again. No change in the shape. Obviously, by scaling, we don't change the shape of the distribution. We just change the magnitude, right? So if you pay attention to the magnitude of this one with this one, this is what we're talking about. Okay, now the next step is to split the data. And we're going to use our regular train test split from scikit-learn model selection. And we have x train x test, y train y test. We're going to do 80% train size and 20% test size. So we can look at the head of the train set. So this is how it looks. These are the random observations. And we use the random state 1000. And we are going to do basically run 4 regressions, right? So the first one is linear regression, and we're going to use it as a benchmark. And for that, I'm not going to use scikit-learn. I will use stats model, simply because the output of stats model is more informative, and I want to talk about the coefficients. So let's do stats model. Feel free to use scikit-learn as well, but if you do scikit-learn, you have to basically make a table for the coefficients manually. So it's more efficient to do it this way. So if you're doing stats model, remember this is what we did in the econometric approach for linear regression. We have to add the constant to our train set and test set to the features. And then once we have the train and test sets x's, we can go ahead and simply train the model. We say from SM, import the OLS. This is the OLS engine. And then we pass the train, Y train, X train, and that's it. We fit the model, look at the summary. Okay, so this is how it's going to look like. So a simple, basically linear regression model is going to give us this. You know, W1 is 0.53, W2 is 0.1, W3 is negative, W4 and W5, they're large and they are, well, actually they're not significant, but that's not the case. We're going to see, can we do penalized regression to get rid of these two coefficients for us, right? So that's the goal. And so this is our benchmark. Then I'm going to compare the performance of the benchmark with the penalized regressions. Okay, so these are the models that we're going to train. And linear regression, ridge regression, lasso, elastic net. Okay, so I actually go ahead and used scikit-learn as well, just one more time, again, to make sure that you know how to do linear regression both in stats model and scikit-learn. And these are all linear in the linear model module from scikit-learn. So we're going to import linear regression, ridge cross-validation, lasso cross-validation, elastic net, and elastic net cross-validation. So we will start with these 4, linear, lasso, ridge, and elastic net. And later in the notebook, I will talk about the cross-validation version of that. In a nutshell, basically, this is going to run ridge regression, but under the hood, it's going to do cross-validation to find the optimal value for alpha. That's it. Yeah, okay. So what I want you to do is to maybe pause the video and look at the documentation of all these functions. Read them at least once. So let me actually pull up them side by side. So this is the documentation for linear regression. Let's look into the documentation for ridge, for lasso. Again, I really want you to go over the documentation at least once to make sure that you understand what's going on. And the last one is our, let's see if I can pull it up. And there you go. Okay, there you go. Okay, so this is, I'm doing it in Google Colab. Now, if you're running it in on your local computer, if you scroll all the way down, you see the links for the documentation. So you can click on the links for scikit-learn documentation, ridge, lasso, and elastic net. So this is basically what I'm looking into. All right, so where were we? Here. Okay, so this is our linear regression. We are quite familiar with that. Let's look into the ridge. So for ridge, look at that. We have alpha. This is our shrinkage parameter. We want to see if we want to fit the intercept or not. By default, it's true. And then what else we need to care? You know, these are some. Basically, this is for make sure that the convergence happens. There's a tolerance level. And yeah, the random state. So this is the objective. This is a loss function, right? So maybe if I pull up the PDF for the ridge regression. So let's go back. There you go. So this is our loss function in ridge, right? You see we have basically mean squared error, and then plus some shrinkage parameter multiply the L2 norm of the weights, right? And this is exactly what we're seeing. Right? This is our mean squared error, and then alpha multiply the L2 norm of our weights, right? Yeah, so that's for the ridge. For lasso, same story. We have mean squared error, and because in lasso it's doing gradient descent, They put 1 divided by 2 multiplied number of samples to make sure that when you're doing the gradient, it's smoother for calculation. And then alpha multiply the L1 norm of weights. And then finally, for elastic net, we know that it's a combination of the two. So let me actually pull up the elastic net. It was this one. So we have mean squared error, and then plus, in the theory lecture, we talked about lambda 1, lambda 2. And then here, let's see, what in the Sklearn, how do they do that? So, but we know that it consists of two components, one for Lasso, one for Ridge, right? One for Ridge. So here, this is our mean squared error. Again, we're adding this 1 divided by 2 to make sure that when you do the gradient, it's smoother. And then now, see how they're doing it. They have something called alpha. This is the shrinkage parameter. Multiply L1 ratio. So L1 ratio means that, so for example, if L1 ratio is 1, it means that let's focus 100% on L1 norm, or the lasso part. If L1 ratio is 0, let's focus 100% on the ridge part, which is L2 norm, right? So we do alpha multiply L1, and then this is L1, and obviously alpha multiply 1 minus L1 multiply the L2 norm. So this is the objective function for the last negative, and as you can see, it's a combination of the two. Okay, so I really encourage you to read the entire documentation for these models and then get familiar with the parameters and the coefficients and the attributes and etc. Okay, so let's go ahead and just create 4 objects for the very basic version of the models, and I'm going to set alpha is equal to 0. Remember, by default alpha was equal to 1, but here, just for learning purposes, I'm going to show what will happen when we set alpha is equal to 0. So let's create 4 objects, 4 models, and then let's train them and then make some predictions. Before I do that, I want you to think about it. When alpha is equal to 0, what are we doing? We're not penalizing our mean squared error objective function, right? It means that the coefficients can be anything. And actually, that's the case that the coefficients of all the 4 models should be the same. Does that make sense? Because alpha is 0, so we should get back to our simple OLS. So let's see that if that's the case. I'm going to create 4 predictions, right? So I call it y hat linear, y hat ridge, y hat lasso, and y hat net. Simply, we have 4 models with alpha is equal to 0. Obviously, for the linear regression, we don't have alpha. And then we fit it using a train set. We make prediction in a test set. So let's go ahead and do that. I'm going to put these 4 predictions in a nice table data frame, and then I will add the actual observations as well. So let's go ahead and look at that one. So this is, for example, for observation number 88 in the test set, y was 1.3. The linear regression predicted this, the ridge predicted this, and then lasso and elastic net. Do you see that all the predictions are the same? Because when you do alpha is equal to 0, basically we're setting them, they're pretty much the same models, right? Okay, and yeah, and we have to see similar coefficients. Let's go ahead and grab those coefficients. So I'm gonna go ahead and basically show you, well, this is what the drop part is doing when I do if I do drop y, and I'm going to keep everything else. So the coefficients are going to be something like this. I'm going to create a data frame called coefficients. We have features. These are the features. And then some coefficients that we get from 4 models. First column, model linear. So these are the coefficients. We are going to extract the coefficients by doing .coef underscore. For ridge regression, for lasso, for elastic nets, and then we're going to stack it all together. This is our coefficient table, right? Or data frame. And again, as you can see, all these 4 models are going to give us exact same coefficients and exact same predictions. Why? Because alpha is equal to 0. Does that make sense? Okay, so if we go back and then, for example, change those alpha, then this is what we're going to do later. Well, actually, I can play around with it. I can say, let's pick a very large value for alpha. Let's do 10. Okay, and we can do 10, we can do 100, and we'll see what's going on. So let's play around with it. So I'm going to run this. I want to focus on the coefficients. There you go. So as you can see, the coefficients for Lasso alpha was so large, and basically because it was so large, it literally penalized everything, and then it says that all the W's should be 0. So this doesn't make any sense, but it's a sign that alpha was super large, so we're here. Let's go back to the Lasso thing here. So probably we are here, right? When the coefficient is equal to 10, when the alpha is equal to 10, we are here. Everything is forced to 0. But we talked about in the theory lecture, the ridge will send the coefficient towards 0, but cannot exactly set them to 0. So that's why we have some numbers for ridge. Okay, so obviously if I go ahead and decrease these coefficients from, I don't know, from 10 to some other number, maybe to 1, we will see something else, right? So let's do that. Well, still 1 is large, so maybe for Lasso, if I do simply 0.1, let's see what we get. And this coefficient depends on what is the magnitude of your target variable and everything. Okay, I haven't created this one yet, apparently. So let's see. All right, there you go. So this is where Lasso is keeping x2 and x3 in the model, and then probably getting rid of x4 and x5, and here it's getting rid of x1 as well. But you get the idea, right? So this is what these models are doing. So I'm going to go back and then set them back to 0, and we will play around with them later on. We need to find the optimal value for these coefficients, which we're going to use cross-validation to find that optimal value. Okay, hopefully it makes sense what we're doing. All right, so we can quickly look at the performance of the model in the test set. For the linear model, I look at if you do dot score by default, Sklearn dot score. For regression, it's going to give you R squared. For classification, it's going to give you accuracy. But this is a regression, so I know that this is going to be my R squared. So R score is very bad. It's negative. It means that it's even performing worse than a simple average model. So if I had nothing but the average, so the performance was better. So, and again, this is not surprising. Look at the predictions. So we are way off. So even our linear regression is way off. So hopefully we can get something better. Okay. So we can just remember these numbers, negative 0.5 and then 2.03. This is the mean squared error in the test set for linear regression. And obviously all these numbers are the same because alpha is equal to 0. Okay. Now let's go ahead and talk about that. Let's replicate that coefficient path, right? So for that, we need to basically come up with some candidates for alpha, right? This is what I'm doing. So I'm going to say, okay, what are these alpha? So for example, 0, 10, 100, 1000, this is log scale. So that's why we need to work with log scale stuff. So that's why I'm doing something like this, 10 to the power. So I'm going to create 100 of these alphas, and it can be between 10 to the power of minus 3, literally 0, to 10 to the power of 4, 10,000, right? And obviously, I need 100 numbers in between these two numbers, right? It doesn't make any sense if I go with equal distance, right? So for example, if I go from 0 to 10,000, and if I divide it by 100, I have to go up every single time by 100 numbers, right? So the first alpha is 0, the second alpha is 100, the third one is 200. It doesn't make any sense because I don't want to go from 0 to 100, just in one step. Probably I want to go from 0 to, I don't know, 0.1, then 1, then something like that. And then as the alpha gets larger and larger, the steps are going to become larger and larger. So what's the way to do that? We can do 10 to the power. We can do log scale, right? So for example, this is what I'm doing. Alpha ridge, 10 to the power, this is a number minus 3 to 4, and this is simply 100. Oh, well, let me actually show you what are we doing here, because usually it's a little confusing. I could do NumPy basically log, and then, but here, this is what we have. Okay, so we go from 10 to the power of minus 3, and then 10 to the power of minus 2.92, and all the way to the 10 to the power of 4. And then we save it as alpha ridge. If I plot it, you'll see what's going on. So these are our alphas, so I call it alpha ridge. And these are the steps, right? So when alpha is small, we take smaller steps, and then when alpha is getting larger, we take larger steps. Okay. All right, hopefully that makes sense, because this is going to give us a smooth path for the coefficient, and honestly we are doing it more efficiently. Okay, so we have 100 of these alpha ridge, and I'm going to put it in a for loop to basically create 100 different ridge regressions using either of these alphas, right? So I'm going to create a coefficient ridge empty list. The model is ridge, and now I put it in a for loop, say go for all those 100 alphas. This is the model. If I do dot set parameters, it's going to change the parameters to whatever you tell. So we are saying that alpha is equal to I, so it's going to go over this for loop 100 times, and then create 100 models and save the coefficient and append them. So this is what we're doing. If I look at the shape of these coefficients, it's going to be 100 by 5, right? Because I have 5 features and then 100 regressions, so that's why every single row is the coefficient when we are using 1 alpha. Okay, now I can plot this. So I have this nice, let's say, matrix or data frame, and then I can simply plot it. So there you go. This is a coefficient path, right? We're not doing anything fancy. We're just, this is the part, plot.alpha ridge and coefficients. Plot the x, which is the alpha ridge, and the y, which is the coefficients, right? And this is how it's going to look like. And we talked about it in the theory lecture. And as you can see, when alpha, and this is log scale, when alpha is increasing, the ridge regression is sending the coefficients towards 0, but not exactly 0. And this is what we saw when we increase the alpha in the Python as well. Okay, so this is a replication of the ridge regression. Now let's look into the elastic net. Let's look into the lasso. Okay, for lasso, we are going to do exact same thing. Here we are going to create the alpha lassos, and this time I'm going to go from 10 to the power of -3 to 10, because this is large enough. And so how do I know that? For this one I should go to a larger number, for example 10 to the power of 4. For the other one I should go to only 10. Well, I tried both and I saw that you know what, we really don't need that large alpha for lasso. It's because it's going to force them to 0 right away after, basically when alpha is equal to 10. So look at that. When alpha actually is close to 1, it's forcing them to 0. And this is what we saw earlier. Okay, so that's why I'm going to say, you know what, let's create this alpha lassos between these two numbers. The same exercise. The model is lasso now. I'm going to change the parameters to alphas and then save the coefficients. Look at the path. This is how the path look like. All right. And as you can see, again, for alpha is equal to, let's say, 1, everything is 0. When alpha is equal to 0.1, so we get something. We get a number for W2, for x2, with the coefficient of x2, which is W2. For the coefficient of x3, it's a negative number. It's good because remember, the true model was a positive coefficient for x1 and x2 and a negative coefficient for x3. And this is getting it. And how do we know what is the optimal value of alpha? Let's do cross-validation. But before that, I'm going to show you the coefficient path for elastic net, and then we will get into the cross-validation. Elastic net, exact same exercise. I just call it alpha elastic net. From 10 to the power of -3 to 10 to the power of 1, and create the coefficients, and then look at the coefficient path. This is for elastic net, and this is closer to the lasso. And as you can see, as you remember, this is a combination of ridge and lasso. And probably L1 ratio here is a large number, because what we are seeing is pretty much the same as lasso. So probably 0.9 or 0.8, something like that. And we're gonna look into that L1 ratio as well. By default it is 0.5, right? But we're gonna look into it later. What is the optimal value of L1 ratio? Okay, so now let's do cross-validation to find these optimal values. Do you remember why we did cross-validation? So we did it for 2 reasons. One, for tuning the hyperparameter, which by the way, we have hyperparameter here. We have alpha and we have L1 ratio. We can play around with them for ElasticNet. And the second reason was to replicate the performance of the model in the test set. So here we're going to use cross-validation to tune the hyperparameters. And if you remember, in polynomial regression, we did it manually. We said that, okay, the D was polynomial degree, and we said, okay, D is equal to 1, D is equal to 2, D is equal to 3. And we tried to use cross-validation for different values of D, and we look at the plot. So let me actually tell you what I'm talking about. So here we did something like that, right? So we look at the cross-validation error, and for different values of model complexity, D was equal to 1 through 10, and say when it was minimized, we said, okay, that was the optimal value for D polynomial degree. Here we can do the same exercise, right? We can do it manually, put it in a for loop, and then go for 100 different alphas, right? But sometimes you want to try 1,000 different of alphas, or I don't know, a couple of thousand, right? There's this built-in function in Sklearn which is going to run things more efficiently, and we're going to use that. So that's why we're going to import the rich cross-validation. So let's look at the documentation if I can pull it up. So yeah, if you hover over the function name, it should let you to click on the documentation. But yeah, so basically this is what this ridge regression cross-validation class is doing. It's a ridge regression with built-in cross-validation. It is built-in. You don't need to write those for loops. You just need to pass the alphas, and then it's going to do the rest for you. You can say cross-validation is by default it's none, but you can do 5-fold, 10-fold, and etc. Okay, so we're going to change the default values of alpha because we don't want to go from 0.1 or 1 or 10. We want to go from all the way from 0 to 10 to the power of 4 for rich, 10 to the power of 3. For elastic nets, well, actually for elastic net and Lasso, we did 10 to the power of 1, right? We don't need to try 10. All right, so we have our own alpha rich or alpha elastic net or alpha Lasso, right? So this is that 100 numbers that we basically created, right? So I'm going to say rich cross-validation alphas. These are the alphas that I want you to use. Again, just a quick reminder. These are the alphas that I want you to use for rich, for Lasso, for elastic net, and that's it. So let's see how long does that take. So under the hood, it's going to go ahead and run this ridge regression 100 times because we have 100 of these alphas, and then find the best one and save the optimal value of alpha in that object, right? So I'm going to go ahead and run it. So it's done. So it seems that for ridge regression, the optimal alpha is 1.29. Okay. Again, it's going to do all those things behind the scene and tell you what is the optimal value of alpha. So here, it's doing this for you, going over all these alphas and find the optimal one. And it seems that it was 1.29 for ridge regression. Okay, great. I'm going to save this. I call it alpha ridge optimized or optimal, and then I'm going to use it later on. Okay. So this model, this object that you trained, have some other stuff that attributes that you can grab. So for example, you can grab the coefficients, right? If I do ridge cross-validation.coef, these are going to be my W1, W2, W3, W4, and W5. And it seems that it was able to send W4 towards 0, but for whatever reason, this is the optimal value of alpha. The W5 is not 0, and actually it's a negative number, but W3 is a large negative number. This is good. W1 and 2 are positive numbers. So we'll see the performance. Then we're going to do exact same thing for Lasso. So Lasso cross-validation alphas are alpha Lassos, 100 of them. Look at the optimal value of alpha for Lasso. It seems that it's very small, 0.004. And again, we are going to save it as optimal, alpha Lasso optimal, and then we can look at the coefficients. So these are the coefficients. And as you see, W4 and W5 are 0. W3 is a large negative number, 1 and 2 are positive numbers. So probably it's doing a good job. And then we're going to do the same exercise for elastic net. So, but for elastic net, there are a couple of things you can play around. One, alphas, and one, ratios, right? So for ratios, so it means that what proportion do you want for using Lasso versus rich, right? So I'm going to start from 0 to 1, and basically we're going to do 0, 0.1, 0.2, and all the way to 1, right? So that's what we have. We're going to try out all those combinations, all these 100 alphas with 10 different combination of L1 ratio, and see which one is going to be the best, right? So it seems that, so it's going to take a little longer. it seems that the optimal alpha for ElasticNet is pretty close to what we have for Ridge, and then so for Lasso. And let's look at the ratio. The ratio is 0.9, so that was not surprising because it's mostly, again, the optimal value says that you have to do 90% Lasso and 10% Ridge. Okay, and we're gonna save this one as alpha elastic optimal, and then we can look at, yeah, we're gonna look at the performance of the model later on. Now these are the coefficients. Again, this is successfully sending W4 and 5 towards 0. Well, actually setting it exactly to 0. Okay, so we're done. So now our job is to look at the performance of the model in the test set, or look at the RMSE and things like that using the optimal values of the hyperparameters. We can go ahead and look at the, for example, test score. I don't know if for any of them it's going to work. So if I do something like this, so for example, if I do ElasticNet cross-validation, there should be a score. Yeah, if I scroll down, there should be, yeah, score, and then I can pass to here. I can pass X, X test and Y test. I don't know, something like that. Yeah, the answer is 76% performance in test set, right? We can go ahead, we can go back and retrain the models using these things as well. Well, actually, let's go ahead and quickly do that. I'm gonna, yeah, it should be fast. So remember, we trained 4 models at the very top here. Now we have some optimal values for alphas and etc. So I'm gonna call, let's see, what was it? Alpha Ridge optimal, and then we're gonna do alpha Lasso optimal, and then let's do alpha ElasticNet optimal, and then I think the L1 ratio was 0.9, the optimal L1 ratio. So these are the optimal values, right? So let's train these models, and then so the Y's are going to be different, obviously, and the coefficients are going to be different too. So as you can see, again, these two were able to set W4 and W5 close to 0. And the reason that these coefficients are pretty much close because it's 90% Lasso and 10% Ridge. Great, so we did it. So this is how to do penalized regression in Sklearn. In the next part, I'm going to do penalized regression using Pycaret. So I will go ahead and install it. If you're doing it, if you're running things in Google Colab, so you have to run this single line every single time when you're working with Pycaret because it's not built in Google Colab. It's a relatively bulky package and there's no need to be built in Google Colab. So we have to go ahead and run it. Okay, so I'm gonna pause the video. This is gonna take a couple of minutes and then we'll come back. All right, we're back. The Pycaret package has been installed. We can quickly check the version. By the time you're watching it, probably it might be different, but right now it is 3.1. Okay, so then let's go ahead and this was a data frame, and we're going to do things in Pycaret, right? So we're going to say from Pycaret regression, import everything. So we want to work with all the models. And then if you remember the Pycaret world, we have to set up the experiment first and then to create some models based on those experiments, right? So I can say setup, and by the way, you can call it, for example, experiment 1, and then setup, and then call everything off of experiment 1. But here, because we're going to work with only, for example, the penalized regression, and we don't want to do different experiments, we're going to keep it like this, right? But at the end of the semester, you're going to see me, when you're doing projects, you can create different experiments. One experiment with pre-processing the data, one experiment without pre-processing, one experiment with different normalization, and etc., right? And you can compare those experiments all in one notebook. And this is a newer feature of Pycaret 3.0, which in the 2.0 it was not available. It's a cool thing. So let's go ahead and set up this experiment, and this is our target variable, random state, train size 80%. I try to keep it as close as possible to what we did in the Sklearn and then compare the outputs, right? Folding strategy is k-fold. We're going to do 5-fold cross-validation, and we are going to normalize things because remember, we want to do penalized regression, and the normalization method is simple standardization, z-score. Okay, let's go ahead and set up the experiment. Now that we have the experiments, we can go ahead and call the models, right? So let me remind you what are the models. So these are the models. Again, if you decided to do, for example, experiments 1, if you decide to do something like this, then from now on, everything you do, you have to call it off of that experiments 1. Okay, hopefully that makes sense. Again, we're going to revisit this thing later in the semester. But for now, let's work with one experiment. Okay, so these are the models. So last time we covered the linear regression. Today we're going to look into the Lasso, Ridge, and Elastic Net. So these are the names: Lasso, Ridge, Elastic Net. And we will cover quite a few of these things throughout the semester. All right, so let's create a bunch of models. So the first one, we're going to create linear regression. Remember we said the 5-fold cross-validation. So what it is doing, it's running the model 5 different times because we have 5-fold cross-validation. And then these are the metrics. And obviously we can look at the average metric, right? So for example, for linear regression, the R-score is, in the cross-validation is 2%. We know that the linear model did not a good job. And do I need to tune this? No, because basically linear regression, there is no hyperparameter to tune, okay? Now let's talk about the other models, Ridge, Lasso, and Elastic Net. But before that, I really want you to double check a couple of things. First, the documentation of Pycaret. If you scroll all the way down, you will see all these things, the links. And second, the model container for Pycaret, because now this is where we are going to tune the hyperparameters using Pycaret. And I want you to see what is the caveat of doing that. Now, Sklearn is more flexible and you can do whatever you want. But with Pycaret, there are some numbers for alphas and L1 ratios that come as a default, and those are not necessarily the best numbers, right? So let's look at the model container. This is something that I want you to get quite used to, checking the source code of the packages. So this is a skill that you should become familiar with. So this is our, remember in Pycaret GitHub, you go to the model containers, containers, models, and then this is regression. If I search for Ridge, and you will see that the Ridge is coming directly from Sklearn package, and then this is the class of Ridge regression. And again, it's directly coming from Sklearn package. Yeah, from Sklearn linear model import Ridge. This is what we did. And then if you scroll down, you will see some what is going on when you're tuning these hyperparameters, right? So what is the dictionary for tuning arguments and the tuning grid? Look at the tuning grid. It's looking into some alphas. Alpha go from 0.01 to 10, and that's it, right? So it means that it doesn't look, for example, if you need the alpha 20 or 30, you don't get it with the Pycaret package. So that's one of the caveats. Be careful, okay? And then I can go back. Now we know what is going on under the hood with the ridge regression in the Pycaret. Let's go ahead and create the model. So it's doing, well, a lot better job compared to linear regression already. It's not tuned yet, right? I can go ahead and tune it. So let's go ahead and tune it. Yeah, the tuned version is going to be, let's see. Yeah, it's going to take a longer time, of course, because it's going. Yeah, it increased the R-square from in the cross-validation from 18% to 20%. So it's doing it. It's doing something, right? It's better than the default values of the ridge regression. Okay, great. We can do exact same exercise for Lasso. So this is our Lasso model. Yeah, right off the bat, this is 16% performance in the cross-validation, and this is our tuned Lasso. So for tuned Lasso, the performance went, look at that, it went from 16% to something less than that, 13%. And you might wonder, scratch your head, hey, wait a second, what's going on? Aren't we supposed to get a better model? And look at that, let's look at the documentation. So if I do Lasso, so this is, yeah, let's look at the, yeah, these are the tuning hyperparameters, right? So alpha, these are the alphas that we're using, and only these ones. So we're not even trying alpha is equal to 1. Or why the steps should be like this. We go from this to this to this. So we're not looking into, so remember the optimal alpha that we got from Lasso, what was it? Actually, I'm curious. It was, let's see, from the Lasso, the optimal alpha that we got was 0.0048. Do we see it here? Obviously not, but so that's one reason, okay, that we got a worse performance. And another reason is that for Lasso, there is not a unique solution. So there's a chance that the algorithm gets stuck in a local optimal. Yeah, okay, so that was the tuned version. Then we can do elastic net. So this is how we train the elastic net, and then tuned version of the elastic net. Again, you can check out the documentation for elastic net. What are the tuning hyperparameters? So let's actually do that as well, elastic net. So if I scroll down, where are the tuning hyperparameters? Yeah, so these are the alphas, and then we should see some numbers for L1 ratios too. Am I in the right place? Let's see if I'm missing something. No, this is sorry, this is another one. Elastic net. Yeah, there you go. So alphas go from 0.01 to 10, and L1 ratios go from 0.01 to 1, okay, by increments of 0.001. So I think L1 is extensive. This is good, but for alphas, usually you have to try out your own. So that's why doing it Sklearn, it's kind of better idea for tuning hyperparameters in general. Yeah. Now we have 1, 2, 3, 4, 5, 6, 7, 8 models. We can put it in a list and say, hey, Pycaret, go ahead and compare these models. So if I do compare models, and then if I pass a list, it's going to compare only those models. If I only call something like this, again, which we're going to do for the final project, compare models, it's going to go ahead and run, I'm not going to run it now, but it's going to go ahead and run all these models under the hood and then compare the performance, right? But for now, we're just sticking to the first 4 models and the tuned version. So let's see what was the best one. And it comes, so this numbers are corresponding to these numbers. So for example, it says that number 5 was your best model. So what is 5? 1, 2, 3, 4, 5. So this is your, oh, sorry, it starts from 0. 0, 1, 2, 3, 4, 5. So this is your tuned ridge regression. So the tuned ridge regression got the best R-square performance in cross-validation 5-fold. Yeah, if you are interested in, for example, MSE or RMSE for whatever reason, your best performers are Elastic Net, number 7, which is the not tuned version. Well, the tuned version. Okay. So that's pretty much it. So here's a bonus question for you. Why we're not able to get the same answer with Pycaret? Remember, our best model was ElasticNet. So in Sklearn, our best model was ElasticNet. In Pycaret, it seems that the best model is, at least in terms of R-square, is tuned ridge regression. Think about it. Why? I already gave you the answer. Okay. Now, the cool thing about Pycaret is the visualization. This is what I'm a big fan, right? So we can do, I'm not going to run this. I'm just going to show you the answers. So we can stick to our best model, which is tuned ridge regression, and we can plot the residuals. We can check the normality of the residuals, and we can check the R-square in the train and test. We can look at the error plot, y versus y hat. So in an ideal world, this should be all lining up. But here, again, this is as good as R-square of 58%. Then an important one is the learning curve, right? So this is our learning curve, and for the train versus cross-validation. So actually, this is something interesting. It seems that regardless of the size of the train set, there is this gap, and this gap is not shrinking. And if you remember from theory lecture, when the gap between train and cross-validation is not shrinking, that's a sign that your model is suffering from a bias, right? Large bias. It means that your model is not capturing some nuances in the data. So you have to think about some other functional form. You have to think about some other models in machine learning. So this is what we learned from the learning curve here. Does it matter if I increase the sample size? This doesn't suggest. So maybe if you had a sample size of 200 and if these two were converging, we would say yes. But as of what I'm seeing right now, probably not. It means that we need to just change the entire engine. Let's change the engine, change the model. And this is what we're going to do later on. Okay. And then finally, making some predictions, right? So obviously I'm going to put it in a nice table. If I call predict model and then put your best model, it's going to do this for you. And this is the Pycaret predictions is this table. Okay, and you can obviously you can extract the very last column by simply calling it, right? So if I do Pycaret underscore predictions, open close bracket, predictions labels, I get access to these labels. All right, that's it. That's pretty much it. This is penalized regression in Sklearn and Pycaret. Please make sure you read through the documentation at least once. All right, now let's talk about the other file, which is exact same code, but now let's use a real world data, which is Boston housing data set. Okay, so now let's do the penalized regression using a real world data set. And I'm not going to even connect this because we're not going to run, I'm going to fly through this notebook. And because this is pretty much the same as the synthetic data, I just wanted to show you how it looks like to apply this penalized regression to a real world problem. All right, so again, I'm going to scroll very quickly. The goal is to predict the price of houses in Boston. And we're going to work with the Boston data set. And as we talked about it in the previous Python lecture, the Boston data set is kind of biased. There's a variable which has something to do with race. And then we're going to drop that. So that's why we're going to drop this variable. And again, the goal is to predict the prices based on some features. So crime, do some pollutions, proximity to the industrials, closing to the river, tax, for example, teacher to students ratio and things like that, incomes and etc. Okay. So again, we have talked about this Boston data set in very detail in the previous Python part. So if you're not familiar with that, please check out the other one, the linear regression model Python. Okay, so then here we're gonna go ahead and split the data. The difference that we're seeing from this file to the previous one in the synthetic data, because this is a real world data, and then when I'm scaling the features, I make sure that I use fit transform in the train set and I only use transform in the test set. So it means that I only use train set to find the parameters of the scalar. What are those parameters? Mean and standard deviation. And then I'm going to use those parameters to basically transform the data in the test set. So that's the only difference between this notebook and the previous one. Everything else is pretty much the same. So again, we have a benchmark model, ridge, lasso, elastic nets. We start with alpha is equal to 0. It's exact same exercise. We look at the predictions, then we look into the coefficients. So these are the coefficients for the model, and then they are all the same, no surprise because alpha is equal to 0. Then we look at the performance MSE test set for linear model. So here let's focus on MSE, not R squared. For linear model, ridge, lasso, elastic net, they're all the same, no surprise. Then we're going to find the optimal value. Well, we're going to plot the coefficient path for ridge. This is the coefficient path for ridge. I have, I think, 12 features, 11 or 12, yeah. And then this is how it's going to look like. Our next job is to use the ridge cross-validation to find the optimal value of alpha. We're going to do the exact same thing for lasso. This is the coefficient path for lasso. And then finally, the coefficient path for elastic net. So here actually, as an exercise, I put in a question for you. So for example, when alpha is equal to 1, which coefficients are going to survive? So I want you to pause the video and stare at this coefficient path and then tell me the answer. When alpha is equal to 1, which coefficients survive? All right, so this is where alpha is equal to 1 here, 10 to the power of 0, 1. So this is surviving, which is L stat. This is surviving, blue one, which is probably crime. It's either crime or pupil to teacher ratio. And then, yeah, both of them are surviving, barely surviving. And then the red one, which is Chast, this is close to that river. And then this one, the brownish one, is RM, right? Okay, so yeah, these are the coefficients that survive when alpha is equal to 1. Great, so then we do the cross-validation, find the optimal alpha for ridge, 4.03, optimal alpha for elastic net, which is for lasso, which is 0.013, and then optimal alpha for elasticnet, which is small number, 0.009. And then we have this elasticnet ratio, L1 ratio of 0.7. So it means that the optimal combination is 70% Lasso, 30% Ridge. Okay, and then the Pycaret, exact same thing. We need to create an experiment. So the target is price and everything is pretty much the same. We're going to normalize it using z-score. And then these are the models. We can look at the linear model. Let's just scroll down and compare them. So this is the comparison. Again, model number 5, which is tuned rich, is the winner for this example as well. And then actually elasticnet is the worst performers. If you look at the, for example, RMSE or R squared. All right, so that's interesting. Well, when I say the worst performance, so the performance is, it's kind of, they're pretty much close to each other, but elasticnet, for whatever reason, it's not doing a good job here. All right, then we can use our winner model, which is tuned ridge regression. We can look at the residual plot. We can look at the error plot. So this is not bad, right? Because we're getting an R square of 68%. And then now this is interesting. This is the learning curve, right? So we have 300 plus observations in a train set. And it seems that in the train set, obviously the performance is going to get worse as the sample size increase, and then cross validation is going to get better as the sample sizes increase. And it's diverging a little bit again. So there are two things going on. So one thing I wish I had, because I like this convergence pattern in general, so I wish I had more information. So maybe collecting more observations is going to be beneficial here. And then number two, again, there's gap. So probably we're missing something, right? So probably this model is not still flexible enough to capture all the nonlinear relationships or pattern in the data. All right. Finally, we can do prediction, and this is our predicted values for tuned ridge regression. And again, as I said it in the previous notebook, if you do, well, we can get to these numbers if I just simply call, because remember guys, this tuned ridge, this is a Sklearn model. So it means that it's coming from Sklearn. It means that I can use all the methods and attributes there. If I do .predict x test, it's going to give me these coefficients. Okay, sweet. That's pretty much it. I hope you enjoyed it. And in the next module, we're going to talk about our first classification model, which is logistic regression. Take care.